So let me do a little bit of a thought discussion about conservative versus non-conservative forces. And think about what happens when I take an object and I lift it up from, this is just meant to be the floor. So let's just say that you're picking up your puppy, pet puppy, to hold it and pet it. I don't know, that looks like a spider. I don't know what that looks like. But you're lifting it up off the floor. Now think about the work done by the conservative force of gravity. If I take this object of mass m and I lift it up a height h, and so now the object is up here, and this is my puppy. The work done by gravity when I lifted it up is equal to minus mgh, because work done by gravity is positive when you move down, it's negative when you move up. So what does that mean? Well, it means that the work done by gravity is trying to slow down the object, is trying to resist your movement of the object. But what it also means, because gravity is a conservative force, it means that when I put the object back down again, right, I go from there to there, sorry, this is now messed up, the object back down again, work done by gravity is plus mgh. So in a sense, what was taken away is now given back. Well, what does that even mean? What was taken away? What was given back? Well, it was trying to take away speed, and now it can give back that speed. Except for the fact that you're lifting it up and putting it down. But it does mean that if your puppy were to squirm out of your arms and drop to the floor, which is fine, it's only a couple feet, and the puppy were to drop to the floor, what does the puppy get back? The puppy gets back velocity, right? That work is turned into kinetic energy. So this brings us to this concept that we can talk about something, the potential to get kinetic energy. When I lift the puppy up this high, it's got the potential to get kinetic energy due to the fact that it has changed its position in the Earth's gravitational field. Puppy squirms out of my arms and drops to the floor, it gets a velocity. Now that velocity is taken away at the floor does negative work to slow the puppy down again, but as it falls, it gets kinetic energy. So in this sense, the gravitational force is a conservative force in the sense that if you, in a different sense than we talked about before, that if you lift the body up, that conservative force gives you a potential energy. It gives you the potential to get energy, as opposed to a non-conservative force. Now just think about the non-conservative force. Let's take my really ugly puppy and put a leash on and pull the puppy. The puppy doesn't want to go outside, it's cold out. Pull the puppy across the floor. Right? So the puppy doesn't want to go outside, you're pulling the puppy across the floor with a leash. And so now there's, right, the reason why the puppy doesn't get going when you're pulling across the floor, it's trying not to, it's curled up and you're just dragging it, or it's having fun being dragged across the floor. But the reason why, even though you're doing positive work, right, the work done by your pull is positive, but the puppy might still end up, being at rest, is because something had to have done negative work. Because remember, positive work means you got kinetic energy. But let's say that the puppy is at rest here, and the puppy is at rest here, the initial and the final. That means that the total work must be zero, right? Because work energy theorem tells us that if the change in kinetic energy is zero, the total work is zero. So if while you did positive work, what did negative work? In this case, friction does negative work, right? So this is just bringing it across the floor, distance s. Friction did negative work. So while you did positive work, friction did negative work in order to slow the puppy down. Just like when you lifted the puppy up, you did positive work, but gravity did negative work, so that the puppy was still not moving when you got it up in your arms, right? That's a really important concept, right? The total work done equals zero just means that, doesn't mean no work is done. It means that no velocity has changed, no speed has changed. So that it may be that you had a positive work and a negative work in order to equal zero. So that's a really important concept. We started at rest, we finished at rest. Doesn't mean no work was done. It means the total work was zero. Okay, back to this. So the work done by friction is less than zero, just like the work done by gravity was less than zero when we lifted up. But here's the question about the frictional force. Can we get that back as kinetic energy? Where did that energy go, right? So we tried to add energy to the puppy by pulling it. Friction took away energy by doing negative work. And so now, can we get that back like we could get the potential energy back from gravity? And the answer is no, because the energy went into heating up the floor, heating up the puppy. It went right, friction. Rub your hands together, you get heat. The energy goes as heat, and we can't get it back in the same way as we can get back the energy when we lift something up in the gravitational field. So with friction, which is a non-conservative force, friction is non-conservative force, you can't get back the work done. So this is the conclusion of the discussion. A non-conservative force, when it does negative work, you can't really get back that work done, right? It's just lost as heat in the floor or maybe something else. With a conservative force, the negative work done stores the energy in a potential energy that you can get back later. So again, would be something like friction, and this would be something like gravity. We've talked about how you lose the energy in friction, the work done by friction, yet the work done by gravity can be gotten back when you move the thing back to the floor. So now I'm going to write this down in equation form. That's what comes next.